Now let us look at the next problem. A cylindrical cavity of diameter A exists inside a cylinder of diameter 2A. Okay, so this radius is A and this radius is E by 2. And this white portion is a cavity. Both the cylinder and the cavity are infinitely long. A uniform current density J, let us say current is coming out of it, and this current density is J, it is uniform. It flows along the length. If the magnitude of the magnetic field at point P is given by n by 12 mu naught Aj, then the value of n is. Okay, now in this particular situation, what we have to do is we have to find out magnetic field at point P, and we will take the magnetic field at this point P as a resultant of magnetic field that would have been there if this was a solid one, there is no cavity. At that case, the magnetic field would have been, let us say, in this direction, B1. Okay, complete cylinder without any cavity. Now if we assume that there is one more cylindrical portion, infinitely long wire having radius a by 2, and if same current density is flowing through this also, then it will also have some contribution of magnetic field at this point, but the only thing is that its direction is reverse. So what happens is that the total current through this portion is I minus I, that is 0, because due to the passage of current in the complete solid cylinder is J and current density is J, and if we assume that one more current is flowing only through this portion in the opposite direction, then the net current in this portion will be 0. Okay, so by superimposing these two cases we can find out magnetic field at point P, and in both the cases we can apply Ampere's circuit law also. Now this point P, if you wish to find out magnetic field for infinitely long wire at a distance r is given by mu naught I upon 2r. Now in this case distance r is a. Okay, and what is the value of current I? Current I is J into pi a square. So B1 can be written as mu naught pi J times pi a square divided by 2 times a. Okay, I'm sorry that we had not considered this. It is actually 2 pi r. Okay, magnetic field is 2 pi r. So we have pi cancelling out, and this cancels out the square. So the magnitude of magnetic field at this point is mu naught Ja by 2. Okay, and it will be tangential in this direction. Okay, that we can understand. So at this point it is in this direction. Or if we see the cross-sectional view, then the magnetic field is in this direction if current I is coming out of it. Okay, now if we take one more current which is flowing in the opposite direction J, and we find out the magnetic field at this point, okay, this distance becomes, this is a by 2 and this is a, so the total distance becomes 3a by 2, and the current is entering into the loop, in the wire. So the magnetic field will be upwards. This magnetic field B2 will be given by mu naught I upon 2 pi r. Now in this case I is current only flowing through this portion, so J times pi mu naught J times area is pi a by 2 whole square divided by 2 pi r, and the distance from the center is 3a by 2. So we'll write 3a by 2. So this cancels out 2. This will cancel out this. A will cancel out here. And finally we are going to get the value of B2 as mu naught JA by 12. Okay. Now the resultant of these two things will be equal to B net will be equal to B1 minus B2, which is mu naught JA by 2 minus mu naught JA by 12. Mu naught JA by 12 will be constant, will be the LCM, and we will get 6 minus 1 or 5 by 12 mu naught JA. So if we compare, the value of n is equal to 5 from the question.